Okay, this is worksheet 2. Normally I don't bring up graph paper because it's kind of messy, but it's warranted for this lesson. Okay, so a lot of this should be review. And so I'm going to kind of go through this assuming that this isn't too bad, and just let me know. If I ever give a video that is too fast for you, just let me know. I'll re-record it. I'll do something different. But if we start off with a function, let's say it's like that. I'm going to benchmark this thing at a couple of points so that I kind of know where I am. Alright, so my function f of x contains, you can pause the video for a second and tell me what those 4 points are. Okay, so for this function that I just arbitrarily threw up onto the screen, I have some x's and some f of x's, and I can make myself a table if that's the kind of thing I want to do. Maybe I do. So I can just say at -2 this guy is 3, at 4 and 5 this guy is -1, and at 9 it's 4. Now we're lucky because we're on this tablet here, and I can easily show you what happens if I want to lift this function a little bit. Okay, so I'm going to actually make these axes a little bigger, just for the reason I want to be able to do this. I want to be able to grab my function, and I'm going to, maybe I'll just make a copy of it. And I'm going to paste a copy of this same function up a little bit. Maybe I'll put it up here so I can erase it to other points easier. So what has happened here is, hold on a second. Point is, I forgot to make it blue. I wanted to make it blue. Okay, so what I'm going to do now is I've just shifted f up a bit. How much have I shifted it up by? You can tell me. 1, 2, 3, 4, 5. I shifted it up by 8. So g of x is equal to f of x plus 8. And that's the way I'd write this, and then I'd put 8. Every y value gets a plus 8 added to it. Okay, so 8 plus 4 should be 12, and so that should be correct. So now I have a blue curve that is g of x, and the original curve was f of x. And so that's how the notation works. Okay, we also might want to multiply. So I'm going to get rid of g for a second so we can pull up another function. And I want you to look at what's going to happen. I'm just going to make the g of x, this time a green g of x, is just going to be 2 times f of x. Okay, so I'm going to try to multiply this by 2 graphically for you. So it's going to go a little bit off the page. But first I think I want to actually I'll just have to live with it. This guy is going to have to stretch so that the -1s go to -2. But I need to stretch it so that the 9,4 becomes 9,8. So I'm going to have to stretch it by twice its size. It's going to be kind of hard there. I think I succeeded. I think I did. Nope, not quite. It does have to go down here. To go a little bit more. Let's see. I think it probably was 1, 2, 3, 4. 1, 2, 3. Oh, I overshot. Okay, let me shrink it just by a little bit. Okay, so then I'm going to go ahead and change these values here to what they really are. And what are they really? The 3 became a 6. The 4 became an 8. The -1 became a -2. Notice that the zeros have to stay put. When you scalar multiply your function, your zeros are going to stay put. This is a problem with this should be coincided. I had a really hard time aligning these, but those two are the same. And what ends up happening is, yep, I tried really, really hard. That is one single point. Okay, All right, so what else can we do? I know we can flip this thing around. Hopefully flipping is easier than stretching. So what happens when you try to flip this thing upside down? So you multiply by -1. And hopefully my computer will let me do this. Oh man! It always does this. The problem is the undo button doesn't mean grab it again because I just lost it. It's just kind of annoying that way. So now my g of x function is, I'm not going to rewrite all those numbers, g of x is equal to minus f of x. Okay, now what else can we do? What else we can do is something like g of x is equal to f of x minus 2. Now what does that actually mean? This can be tricky sometimes, so I want you to sort of pay attention to this one. If I'm starting here at f of x, do I go to the right or do I go to the left? Let's see, we would normally probably instinctively go the wrong direction. What you want to do is you want to think of the -2 as meaning your thing is delayed somehow in time. So if the blue curve happens in a delayed fashion, it moves to the right. Because as time progresses, then that is indicating something is delayed. When the time at which it arrives is later, then the thing itself is delayed. So you're looking at the x value on f where this happened, say, 2 seconds ago. So you're 2 seconds. G is 2 seconds delayed from x. Then the graph moves to the right because it's delaying. And if you wanted to go the other way, you would, of course, say, okay, fine, I'm talking about plus now. I'm talking about plus f of x plus 2. In other words, that function is advanced by 2. It is happening earlier because it is somehow advanced by 2 time units. Okay? So I want you to think about what's going on inside there is talking about somehow the speed at which g, or whether it's earlier or late, or fast or slow. So if you say f of x plus 7, then this guy means we are early. And if it's -7, it's going to be late. If it's late, it's shifted to the right. And now if you're going to compare whether it's fast or slow, think about it this way. This is kind of like the speed at which f is traveling, right? So in this case, you're traveling twice as fast. And so everything's going to get compressed. The graph itself is not going to stretch. It's actually going to compress because the speed has gone up. So I want you to think of that as the speed at which you're running the video of the other graph. Okay, so let me see if I can set that one up for you. Okay, so this is our f. I got rid of those numbers that were just driving me nuts. G is equal to f of 2x because this graph is twice as fast as g is going twice as fast as f. And so what you're going to notice about this kind of shift is that wherever f is at 0, g will be at 0. And then it's just sort of like an accordion. It either compresses or it stretches. So if you wanted like k of x as a new graph, f of x over 2, it's actually going to stretch the whole thing out farther so it goes like that. I'm not going to line that one up for you. Okay? But that's what would happen to that graph. Okay, I just got rid of that graph paper because it was driving me nuts. And now we're back to normal paper. And we want to talk about graph compositions. Compositions of expressions and stuff. So for example, we did this in the last video where we said f of x equals x squared and g of x equals 3x plus 1 or something. I don't remember what it was. That just all that nesting. If you say f of g of f of something, let's say 1, let's see what happens. F of, and then you have to figure out, well, what is g of f of 1? I don't know. Well, first I need to find out f of 1. So what is f of 1? F of 1 is just 1. So this guy turns into a 1. What is g of 1? Well, it's a 4. So this guy turns into a 4. What is f of 4? Why, that's 16. Okay, so you just work your way starting in the inside and working on the way outside. Also, you can multiply these things together. You could say f of 3 times g of 4, and then you would calculate them both separately and multiply them together. And you proceed as you would expect. Okay, next idea. General shape on advice of how polynomials progress. So this is the kind of thing that you may have picked up naturally, or you may need to be told explicitly. So I'm just going to tell you explicitly in case it's something that hasn't been covered at some point in your past. Lines are basically what you would expect. And when you cross the axis with a line, it just is not very exciting. This is your standard root. But you also have other shapes, and shapes can sometimes occur on the axis at a root or off the axis, but you have like a parabola shape. These are all how you would sketch a parabola, and parabolas can cross the axis twice, or you can have a double root on a parabola, or you can have no roots, no real roots. If you have no real roots, as you know, it's a complex conjugate pair of roots. So the roots don't disappear, but they go into the complex world. Okay, so that's what a parabola typically looks like. Cubics are pretty cool. We don't spend enough time talking about how cool cubics are. One thing that's cool about cubics is that they're always symmetric about their center point. You can think of a parabola as having a vertex, and that's kind of its center point. Well, a cubic always has kind of a central point too. It's always a point of inflection in a cubic, and you can spin that thing around 180 degrees. So sometimes students will draw things like that and claim it's a cubic, and I'm like, no, it's not. There's no point of rotation. You can't rotate that thing. You have to try to make this thing symmetric. Once you've committed to one half of your cubic, try to make the other half of your cubic look roughly the same. Those humps are always the same size, and if the humps are missing, that's fine, but you still always have that point of inflection. So that you can have a point of inflection that's on an upward slope, a point of inflection that's horizontal, and you can have a point of inflection that's on a downward slope, or the whole thing can flip around. You can have this kind of cubic, this kind of cubic, this kind of cubic, and those are the only possibilities. Those 6 possibilities, but in all cases, the cubic is always symmetric about its center point. Next, you want to know a little bit about quartics. Quartics can have a flatter root. So like if you look at this function y equals x to the 4th, you will recognize it because it looks kind of like a parabola, but it's like a flattened parabola. So the root just kind of sticks down because it just kind of squishes. Looks like x to the 4th. But x to the 4th can also do this kind of thing, or this kind of thing, or sometimes it does some of each. Okay, so there's all different ways that quartics can look. You're just always just counting the wiggles, but the point is some of the wiggles disappear into the complex plane. So if you have I tell you this is a polynomial, you can literally count the wiggles. So you think, well, this piece looks like a parabola, this piece looks like a cubic. So count it this way, say line. So 1, 2, 3, 4, 5, 6, 7. So that's, if you tell me it's a polynomial, it has at least degree 7 based on how many wiggles it has. But even if your wiggle looks like this, that's really a degenerate form of one of those. So you can count flattened out parts as if they're basically 2 wiggles. Okay, what else? Logarithmic curves are going to look like this. Exponential curves are going to look like this. Logarithmic curves are going to look like this. And I think that's enough to get you through your worksheet. Look forward to seeing you in class.